All right, welcome to the applications video. So there's some really cool applications, but they can be tricky problems. We're just going to do the problems from the book. Let's do number 66 to start. And number 66 says it wants us to find the dimensions of the rectangular corral producing the greatest enclosed area, given that we have 200 feet of fencing. So logically, you may already know the answer to this problem, but I want to show the process with a simpler version of the problem, and then let's do harder problems to solve these, okay? So dimensions of the rectangular corral doing the greatest area given 200 feet of fencing. That's going to be our first step, is drawing a picture and writing down information. Okay, draw a picture and write down relevant information. So the only real information that we have is a rectangular closure. And we know we have 200 feet of fencing. All right. With this picture, include variables. Let's name variables in the picture. So in the picture, when we're trying to figure out dimensions of a corral, we're going to have a length and we're going to have width. You can call these whatever you want. L and W make a lot of sense. X and Y are my preferences. L and W is great though. Second step. What are we trying to do? Gosh, I still don't know what's happening here. Why this keeps scrolling. What are we trying to do? I feel like I'm losing my mind sometimes. Sorry. What are we trying to do? Greatest enclosed area. We're always going to be trying to find maximums and minimums with these applications. Greatest enclosed area. But what are we maximizing? Or minimizing? That's what we're going to say. We want the greatest area. What's the area? Area is going to be X times Y. So answer, what are we trying to maximize? What are we trying to minimize? And use an equation or a formula. It's rectangular area, that's X times Y. This is what we're trying to find the maximum of. The next step we're going to do, we haven't used this yet. Write down information using, like put this in terms of math. Put this 200 feet in terms of math. To put the info in terms of our variables. So what does 200 feet of fencing mean for us? If we're making a rectangular enclosure, that means this side plus this side plus this side plus that side has to be 200 feet, right? We can't fence in anything bigger than an enclosure with 200 feet of a perimeter. So that means for step 3 that X plus a Y plus another X plus another Y has to equal 200 feet. Or we can make this look a little nicer. 2x plus 2y equals 200. Or we can make it even look nicer by dividing everything by 2, but let's not overthink it. That's step 3. So now we have something we're trying to maximize. This is what's called an objective function in higher level mathematics. Let's not worry about it now. And we have a constraint. Because, right, if we didn't have this requirement, if we didn't have 200 feet of fencing, we could make an area as big as we want. I mean, according to the problem. Obviously, in real life, there are other concerns. And I'm not going to get into that either. Sometimes application problems can be a little silly. So step 4. And again, this is called the constraint. solve the constraint equation for any variable. It doesn't matter which one you choose. Just choose a variable, solve for it. I'll solve for y because that's what we have more experience with. So to solve for y, let's subtract 2x from both sides. That's going to give us this 2y equals 200 minus 2x. Divide everything by 2, and we get 100 minus x. That's step 4. Step 5. Let's write step 5 over here so you can see it a little bit better. Plug in the result into what you're trying to maximize or minimize. Mining? Is that a word? Looks like mining. Well, you're maximizing or minimizing. So what does that mean? That means if y is equal to this, we're plugging that into y. And I really do want this all on the same page here. Let's scroll down. No, let's not do that. We'll use the next page. So plug that in. Area, right? Area is x times y, but we also know that y is 100 minus x. Y is 100 minus x. And now look, we have a function of a single variable. This is a quadratic function. And that brings us to step 6. Find the maximum or minimum of this quadratic. We know how to do this. We've been doing this all section long. Let's get it in general form. Distribute that x. We're going to get 100x minus x squared. Put the x squared term first. This is general form. We know how to find the maximum or minimum of this. First off, right, we do know there is a maximum. The a value is negative. This is a parabola that opens downwards. Depending on what the side length x is, this tells us the area. X is length, area is a. So how do we find the maximum? We find the axis of symmetry. Axis of symmetry is when x is equal to negative b over 2a. That's negative 100 divided by 2 times negative 1. Axis of symmetry is when x is 50. Well, the vertex, when x is equal to 50, a is going to be negative times 50 squared plus 100 times 50. That's negative 2,500 plus 5,000. The maximum area, and x is in feet, area is in feet squared. And then we're almost done. Sometimes you have to use a constraint to find the other variable. Just make sure you answer the question. So in this problem, it said find the dimensions that maximize the area. Well, I found one of the dimensions, and I found the maximum area, but we didn't find the other dimension. Right? Y, we said, was 100 minus x. If x is equal to 50, then the other dimension, if x is the length, y is the width, is 100 minus 50, or just 50. So that gives us the optimal dimensions for maximum area. 50 feet by 50 feet. And if you know much about areas in general, yes, the maximum area is when it's a square. And this is a square that has a perimeter of 200 feet. So we're going to be using this process to solve application questions. All right, let's look at one more. Okay. And then we'll do another one on the selected homework problems video. Do one more. This is going to be number 70. One day I will solve the mystery. Among all pairs of numbers whose difference is 12, find the pair with the smallest product. Ha! I'm losing my mind over here. Hold on, I've fixed it by refreshing before. I didn't know why it worked, but I fixed it by refreshing before. Also, make sure we solve the problem, find the dimensions. Yes, we found the dimensions. Number 70. Let's follow step-by-step instructions. Step 1. Draw a picture and write down information. Name the variables in the picture. Well, we're just finding a product. There's no physical thing here. There's no picture in number 70, sadly. But we can name the variables. We need two numbers. Let's say our two numbers are x and y. You could call them whatever you want. All right, what was step 2? What are we trying to minimize or maximize? And what's the formula for that? Find the pair with the smallest product. What's the smallest product? Product just means x times y. That's step 2. Step 3. Put the information that we wrote down in terms of our variables. What is our requirement here? Oh, we didn't write down our information. Two pairs of numbers whose difference is 12. That was the information that we didn't write. The difference means subtraction. So in step 3, it says, put information in terms of our variables. That's what this is. This is our constraint. This is what's known as the objective function. Step 4, solve the constraint for any variable. We solved for y last time. We could solve for x this time. It doesn't matter. We just need to solve it for something. Solving for x is easier here. X is y plus 12. Step 5, plug in the result into what you're maximizing or minimizing. We're plugging this in to x, the objective function. So now p is equal to x, which is y plus 12 times y. So p, let's distribute, becomes y squared plus 12y. This is a quadratic function. Step 6 was find the maximum or minimum of this quadratic. So this quadratic function is a positive a value. It goes up. There is a minimum, which is good because we do want that smallest product. How do we find the minimum? We find the minimum on the axis of symmetry. Normally we write axis of symmetry as x equals, but notice our variable here is y. So it's going to be y equals negative b over 2a here, because we don't have any x's, not in this equation. That's going to be negative 12 over 2 times 1, or when y is negative 6. And we could find the smallest product by plugging this in, or we could do it later. You can find the smallest product whenever you want, but either way, this is going to be important. Step 7, use the constraint to find the other variable and make sure you answer the question. So let's use this constraint equation. Y is negative 6. Add 12 to this. X is going to be, hold on, I'm losing my mind here. X is going to be positive 6. So yeah, it never said these things had to be Never said these numbers had to be positive. All right, let's read the question, make sure we have the answer. Among all the pairs of numbers, find the pair with the smallest product. So our answers are 6 and -6. That's the pair with the smallest product. What is the product? Well, what's 6 times -6? Product is -36. Choose any pair of numbers that are 12 apart. This is going to be the one that gives the smallest product. Right? And we can look at that, right? If we did increase them by, or decrease them, right? It'd be 5 and -7. Well, that would have a product of -35. That would be bigger. Went the other way. 7 and -5. Well, again, anything you choose is going to have a higher product than -36. So that's our answer. Let me know if you have any questions, and remember, I do another application problem in the next video. So if you're still unsure on these, we'll do it again.